Our goal in this video is to see how to factor matrices. Um, Given a matrix A equals just a square matrix A, we want to factor it into two matrices. One matrix that has zeros above the main diagonal, so that would be a lower triangular matrix, and one with zeros under the main diagonal, so that would be an upper triangular matrix. So that would be lower and upper. So we're going to label those as L and U for lower triangular matrix. So we're going to have stuff here and there and here and there, possibly zeros, but here and there, but for sure zeros on the other side of the diagonal. Furthermore, we want to have ones on the main diagonal. This one automatically will have ones on the main diagonal because of the way we're going to construct the lower triangular matrix. The upper triangular matrix will not have necessarily ones on the main diagonal. So in order to have ones on the main diagonal, we have to factor out some constants. So we're going to further factor this into three matrices, L, a diagonal matrix, which will take care of the non-one elements in the main diagonal, and then the upper triangular matrix. So we're going to have a diagonal matrix, which will have zeros everywhere except possibly in the main, well, actually, except in the main diagonal. And those numbers are oftentimes not going to be one. And what we gain by that is that we're going to have an upper triangular with ones on the main diagonal, some stuff up here, and zeros, that's why it's upper zeros, upper triangular. And then we're going to have ones there, lower, so zeros on the entries above the main diagonal, and then some stuff, some numbers here on the lower. So we're going to have numbers, some of them may be zeros, ones, zeros for sure, zeros and zeros, some numbers. So here we can put some question marks, I don't know what, but some numbers. Here, ones for sure, and then zeros and numbers. So this is our goal. Our goal is to be able to write a matrix into two such matrices rather, or into three such matrices. So this would be a further step from this one. We're going to do that by elimination, because the original matrix may or may not have zeros in the places where we want them to have zeros. So we're going to start getting zeros here. Now, this is going to be a long process. It isn't a simple thing to do, just here's the answer, or just follow this formula. It is not going to be like that. It's, I don't know how long one problem will take, maybe 20 minutes or something like that, because it is a process that we have to follow. So just be aware that this is not an equation. Please follow it. With a long problem, a problem that takes 10, 20, 30 minutes, sometimes it is hard to keep concentrated on that one problem. Please try that. If you're watching the video, you might want to pause for a moment, take a little walk, around the kitchen or something, come back and, think about what we've done, reproduce it perhaps, and then keep watching the video until we get to finish it. So keep in mind that the process to obtain the factoring of a matrix is not simple or trivial. if we are thinking of coming up with a shortcut, I'm just going to try to, like something like a quadratic equation. Just tell me what A, B, and C are, and then I'm just going to plug in A, B, and C, and simplify, and boom, there's the answer. No, it doesn't quite work like that. So let's start with one example. So this is going to be example 1. And let's start with this 1, 7, 8, 2, 41, 13, 4, 73, 35. Okay, so there is our matrix A, and our goal is initially to factor it into 2 matrices. One is going to be labeled lower L for lower triangular matrix. The other one is going to be upper triangular matrix, U for upper triangular matrix. This upper triangular matrix initially will not have necessarily ones in every element of the main diagonal. So because of that, we're going to split U into 2, this initial U into 2 matrices. This is going to be unitriangular, like unicorn, kind of unitriangular upper matrix, or upper unitriangular matrix, because it will have ones in here, and this one will already have ones in there. And so this one is going to be easy to figure. It is going to be easy to split that. That's going to be one step. Coming up with this is going to require a few steps. So here is the example: 178, 241, 43, 473, 35. And then let's start factoring this out. So we're going to do this by elimination. We're going to eliminate the 2 first via a multiplication. So, okay, so what is the strategy? Maybe we should write down the strategy. Okay, strategy. So we're going to find a matrix E. Well, I'm going to label it E1. E for elimination, that's why we're using E. So a matrix E that multiplied with A, E1, will take care of that too. We'll annihilate this too. So we're going to have 1, 0, and a bunch of other numbers. Then we're going to annihilate the 4. And that's going to be done with a second matrix. Okay. Now, when we do that, those two are going to be quite similar, and they're going to be derived from 2 and 4. That's not a big issue. When we do that transition and eliminate those numbers, the 2 and the 4, that is going to cause those numbers to be different. Yeah, that is an important thing. So as we transition from one column to the next column, if we do this systematically from the left to the right, wiping off one column and then moving on to the next column, those numbers are going to be different. So we do not know what numbers are going to be in here in advance. I don't know what they will be. I have to actually do the computations through the process of finding those 2 first and obtaining the matrix to get to an answer. Anyway, so we're going to find a third matrix that is going to get rid of this number. This number is not going to be 73. It will be something else after we perform those 2 eliminations. So there's going to be a matrix E3. After doing that, all of those entries will be 0, 0, 0, 0. And we're going to have a nice upper triangular matrix. So that's going to be an upper triangular matrix. Okay, so here's the trick. We don't want to find this. Well, yeah, this is part of the problem. But we also want to find the other matrix. This U, by the way, will be that U. And now we want to find this L. Well, that L is not just those 3. It's not all of that. That's 8 times that. We want to end up with A. We want to end up with A equals 2 matrices multiplying each other. One is going to be lower triangular, and the other one is upper triangular. Well, this is going to be upper triangular because that's the construction that we are getting rid of that and that entry. So we will end up with an upper triangular matrix. How do we come up with the L? Well, here's the trick. We have to take the inverse of those 3, and there's a couple different ways to go about it. we can consolidate this into a big giant E, and then find the inverse, and that's going to be labeled our new L. So, or you can take those one by one, find the inverse of each one of those one by one, and that's going to be the inverse. So there's a couple of different ways to go about that. But that, what I'm trying to tell you, that what I want to advance is that we got to go through those steps, and then there's one further step to get to the L. Once we have L and U, then we're going to be at this point, and then going from here to here, we're going to have a total factoring into triangular matrices. I'm going to call it total just right now, when we have ones here, and then not necessarily ones on the diagonal matrix. So that, I'm explaining why this is going to be a process, because there's a step 1, a step 2, a step 3, a big step 4 before we get to this point. And there's no really a good shortcut, or maybe there is, I don't know. Let's go through this. So the first thing we want to do is figure out how to eliminate the 2 using a matrix. And that's actually not difficult. So 1, -2, 0, 0, 0, 1, 0, 0, 1 will do. So if we multiply this by A, 1, 7, 8, 2, 41, 13, 4, 73, 35, then we will be able to do that. By the way, this should be a review of the previous video. We already have done this kind of thing to eliminate. So let's see. This row indicates that we're going to pick the first entry on each one of those columns, and then nothing else. So this product will be 1, 7, 8 on the first row when we multiply those 2 matrices. And then we're going to have -2 plus 2, 0 plus 0. So that's going to be automatically 0. -7 plus 41. I believe that is 34. Let me, oh no, that is -14. I was subtracting wrong. -14 plus 41. I'm going to do that computation. 41 minus 14. So 11 minus 4 is 7. 3 minus 1 is 2. So we end up with 27. Okay. And then -16 plus 13, well, that's -3. And then we're adding 0 times 35 with that. So that doesn't count. And then we are picking up the third element on each one of the columns. So we got 4, 73, 35. Okay, so this one matrix is our first elimination matrix. I'm going to call it AE1, the first elimination matrix. So we're closer to an upper triangular matrix. This is not an upper triangular matrix because we should have 0, 0 on those entries. Our original matrix, which is this one, does not have any zeros at all whatsoever. So by having this 0, we're getting closer. We're not there yet. Okay, so now we need to find a second elimination matrix. We can label it, I mean, we want to get rid of this 4 using this 1. So the column here would be 1, 0, -4, and then the rest will be an identity matrix. And we multiply with this new matrix. Now, this is not A. This is a new matrix that is getting closer to becoming an upper triangular matrix. So 1, 7, 8, 0, 27, -3, 4, 73, 35. Let's see if I can squeeze this in one line. The matrices are large. But let's see. So again, this row picks the first element on each one of the columns. So all we do is copy the column down, 1, 7, 8. The second row picks the second element, excuse me, on each one of the columns. So we're going to end up with 0, 27, -3. Then this row takes the first row and subtracts 4 times of it from the third row. So yeah, this row times -4 plus the bottom row. Okay, so let's do this column by column though. -4 plus 4, 0. -28 plus 73. 73 minus 28. So I'm using this little space to do some side computations. 13 minus 8 is 5. 6 minus 2 is 4. So we end up with 45. And then -32 plus 35 is 3. Remember, we're doing sort of the dot product. Actually, we're doing the dot product between this row vector and this column vector. So the 0 causes us to skip this element here, -3, because we're just multiplying by 0 and then adding 0 doesn't count. Doesn't really contribute anything to the total output. So -32, 0, and 35 added together gives us 3. All right. So now we're closer to an upper triangular matrix because this matrix has 2 zeros. Remember, we started with no zeros on the lower end of the original matrix. This is the original matrix A. We multiplied with E1. We got this matrix, which is closer to being upper triangular. Now we have an E2, and we're going to label this as elimination matrix number 2, which is taking this matrix, which was closer, and turning it into a matrix that is even closer to becoming a upper triangular matrix. All right. So now we got to get rid of this 45. But if we were not thinking this through, let me start out with these rows. 0, 1, 0. All right, 0. If we were not thinking this through, we would say, oh, shouldn't I put a 45 there, -45, because after all, that's what we did up here, 2. So we did -2, 4, -4. Well, 45, -45, not so fast. The reason why the 2 and the -4 worked so well is because we already have a 1 in here. So remember what we are doing. Let's see, when we are getting rid of this. This row says take essentially this row, multiply it by -2, so there's a 1, times -2 is -2, and add this row. So that was easy to do. I mean, it was easy to obtain a 0 because this 1 is not affecting the multiplication. All we have to do is do -2 plus 2, and that will do it. Here we have a 27 instead of a 1. So we have to get rid of the 27 to convert that into a 1, and then multiply it by -45, and that will actually work out. So yes, we have to put -45, but we also have to take into account the 27. So we divide by 27 to get the 1, because this row has no 1 in the main diagonal, and the main diagonal of 1, oops, up here, is the one that helped us, well, this one, get rid of the 2, and that 1 also helped us get rid of the -4. So now when we move on to this column, we should have a 1 in the pivot, in the pivot column, in that pivot column, but we don't have a 1. So the way we handle that is by compensating and dividing by 27. And the rest is fine. So we are going to multiply with this other matrix, 1, 7, 8, 0, 27, -3, 0, 45, 3, Okay, and we should obtain an upper triangular matrix at that point. Now, before we do that, notice that this 45 over 27 can be simplified. We can factor out a 9, so we end up with 5 over 3. It's way easier to multiply by 5/3 instead of multiplying by 45 over 27. And there's no harm done with multiplying by 5 over 3 because they're the same number anyway. Well, they're both negative. So this row picks the first row up here and leaves it alone, 1, 7, 8. This row picks this row and leaves it alone, 0, 27, -3. This row doesn't use this row at all. It multiplies the second row by -5/3 and adds it to the last row. Okay, so 0 multiplied with anything added to 0 doesn't affect it. It's just 0. 27 multiplied by, well, let's think of it this way. I guess the 27 does, this form of the fraction is more convenient when we have 27, now that I see that. So 27 times -45 over 27, of course the 27s simplify and we end up with -45, which then we're going to add to 45, and that's going to cause us to have 0. Now we got to be more careful with this. -3, here, instead of using this form of the fraction, I'm going to use this form. Oh, how convenient. -3 times -5/3, the 3 simplify. The negatives also undo each other, so we end up with 5. Okay, so remember our goal. Let's go back to our goal. What is our goal? Our goal is to split A, our original A, which is this guy, into 2 matrices, the upper triangular and the lower triangular. Now, we don't have a lower triangular. We have an upper triangular. That is our U. Our U. So we are finished figuring out what this matrix is. This matrix is not that obvious. We have to do some more work to figure out this. Okay, let me go back to this kind of computation. Or let's go back to see what has expired. We have A, we multiplied with E1 first, remember? That was original A, multiplied with E1, first elimination matrix. Then the answer got to be multiplied with a second and a third elimination matrix. We're going to label this one as elimination matrix number 3. So we multiplied with E1, E2, and E3, and we did obtain U. But we don't want just U, we want the L, and the thing is the L is not showing up here. I'm going to show you 2 ways to go about doing this. The easy way and the fun way. I don't know if one is fun and the other one is easy, and I don't know if one is easier than the other. I was just trying to make a joke there. So what we do, let's do the 2 methods. So one method is to find the inverse of this guy and multiply on both sides by that inverse. On both sides of the equation, not on both sides of the matrix. So we're multiplying on the left. So from this equation, we multiply everything by the inverse of E3 on the left, E inverse 3, E3 inverse times a U, there we go. Now those 2 will cancel, that's the whole point. They're going to end up with the identity. So those 2 become the identity, and so we can disregard them because the identity times anything else is going to be that anything else. All right, so now we got, so disregard this circled product. So now we got those 3 equal to those 2. And I just want to have A by itself. Remember, go back to the goal. The goal is to have A split into 2 matrices that are multiplying each other. So multiply now Let's write this down. E2, E1A equals E3 inverse U. Now we're going to multiply by E2 inverse on the left. E2 inverse E3 U. So those two are going to simplify to the identity. The identity times that is going to give us the same thing. But now we got E2 inverse, E3 inverse, that's an inverse, U. And then we repeat that process one more time. E1 inverse. So we're going to multiply on both sides of this equation by E1 inverse. On the left, it is very, very important to realize. So those two are going to simplify. On this side of the equation, we're going to have E1 inverse, E2 inverse, E3 inverse U, and that's going to be A. So again, E1 inverse, E2 inverse, E3 inverse, U. Now, if we multiply those three, we're going to end up with our L. And we're going to be very happy because then we're going to be finished with this multiplication, with finding out the upper triangular matrix as well as the lower triangular matrix, whose product gives us A. Okay, so this process, we already know E1, E2, and E3. They were that matrix, this matrix, and this matrix. But now we need to find the inverse. The inverse of those matrices is fairly straightforward. Okay, so inverses of E1, E2, comma, and E3. So those inverses, the inverses for those matrices. What we are doing in this, with this matrix, let me write it down. 1, 0, 0, negative 2, 0, whoops, 1. I get carried away sometimes. 1, and 0, 0, 0, 1. Okay, so this is E1, and we want to find its inverse. Now, what we are doing with this matrix is adding twice this row to this row. And to undo that, we're adding negative 2 of those into this row. Yeah. So to undo that, we can add 2 of those into the same row. This is what I'm trying to say. 1, 0, 0, 2, 1, 0, 0, 0, 1 should be the inverse of this matrix. So I'm proposing this is the inverse. How can we be sure? Well, just multiply them together. And if we get the identity, we have it. So 1, oh, this just picks the first row. So the first row of this matrix remains. This one is the one that changes things. Negative 2 plus 2, 0. That's the whole point. But then we have 0, 1, 0. And then 0, 0, 1. Nope, 0, 0, 0 because of this 0. So we got 0, 0, 0. And then we're picking just the third row, 0, 0, 1. This is the identity. Identity. So that means that this is the correct inverse of this guy. Okay, let's put that on the back burner. Let's quickly check 0, negative 4. Remember our E2. E2 is in column. The columns are 1, 0, negative 4. And then we have the other columns of the regular identity. So what do you think the inverse should be? Well, if you're guessing 104 for the first column, I think you're going to be correct, but let's double check. And Yeah, and we should. So first row remains as is, second row remains as is. For what I mean by that of this matrix. Third row, okay, so negative 4, 0, 4, that gives us 0. And then 0, 0, 0, and then 0, 0, 1. Sure enough, we got the identity. So indeed, this is the inverse. And then we think of a E3. What was E3? Oh, it's in here. E3 is the one that has negative 5/3 here. Negative 5/3. That 5 looks funny. 1, 0. And then we have, if you had to guess what the inverse will be, 0, 5/3, 1. I think that's it, but let's double check. And sometimes you can check quickly, by inspection. The first two rows are going to be the same, so we're good there. And then here we got the 0, 0, 0. So that's going to be 0, 0, negative 5/3, plus 5/3, 0. And then we got a nice 1. So sure enough, those three, the second ones of those products are going to be the identities, or rather the inverses of E1, E2, E3. And those are the inverses. Well, according to our diagram here, in order to find the lower, we have to multiply together the inverses, those inverses, E1 inverse, E2 inverse, E3 inverse. Well, that's E1 inverse, that's E2 inverse, that's E3 inverse. Why? Because when we multiply by E1, E2, E3 respectively, we end up with the same identity. So that means those are inverses. Okay, so let's multiply them together. I'm getting too many papers and I don't want to mix them up. So, okay, so we're going to multiply E1 inverse times E2 inverse times E3 inverse. And that means 1, 0, 0, 2, 1, 0, 0, 0, 1 multiplied with 1, 0, 0, 0, 1, 0, 4, 0, 1. Remember, that's E2 inverse. And then we're going to multiply with 1, 0, 0, 0, 1, 0, 0, 5/3, 1. Remember, the matrices that have negative 1 here, negative 5/3 there, negative 4 here, and negative 2 are the original elimination matrices. Yep. The original ones that we multiply with A to get the upper triangular, but we don't want those with the negatives. We want the ones that are the inverses, because we want to end up with A as two matrices, and that's the matrix we're about to find right now. Okay, so let's multiply this out. First row of this matrix stays as is, so we're going to end up with 1, 0, 0. Let's look at the second row. 2, 0, 0. 0, 1, 0. So that is 1, and 0, 0, 0. And then we have 1, 0, 0, 4. Interesting. 0, 0, 0. And then 0, 0, 1. Okay, so that was the product of the first two. We still have to multiply by this guy. So those two multiply to this. This one was just waiting there. Okay, when are you guys going to be finished multiplying each other? That's kind of that matrix is thinking. And now that they're done, okay, now it says, okay, now let's multiply. So 1, 0, 0, and then 2, and 0, 1, 0, and then 0, 4, 0, 0, 5/3, and then 0, 0, 0. And notice that this matrix is lower triangular. So this is our L. Okay. So when I will ask you to find the factoring of the matrix A into the lower and upper triangular matrices, well, we have all the pieces now. So the original A is this one, 1, 7, 8, 2, 41, 13, 4, 73, 35 is equal to this guy, 1, 0, 0, 2, 1, 0, 4, 5/3. I just realized I made a mistake. That should be a 1. I'm just going to scratch it off. 1. It is not 0. We have to have a diagonal of 1s. And what about the upper triangular matrix? It's not in here. Now, those are just the E's. That was just checking the previous page that we have inverses. That was just the strategy showed a little more extensively. Where is our upper triangular? Oh, there it is on our first page of computations. U is this guy, and we can tell because there's zeros here. So we have 1, 7, 8, 0, 27, -3, and 0, 0, 5. Well, so there is the decomposition of the original matrix A into lower triangular matrix and then upper triangular matrix. Why is this lower? Because it has zeros above the diagonal. And this is upper because it has zeros below the main diagonal. Now, if I was doing this as part of a test, I would, before I turn that in, and if I have time, I would definitely want to double check that the numbers are correct. Okay, so 1, yep. Now I gotta get, well, this means we're gonna pick up the first element in each one of the columns, 178, 178, 100, so that works. Okay, now let's continue here. 2 and 0 and 0, 2, that works. 14 plus 27, 41, yep, that works, and then 0. 16 minus 3 is 13, plus 0 is 13. So second is good, second row. 4 and 0, 4. 28. Okay, so that's 28. I'm going to think of that and, okay, put it in my short-term memory. Okay, and I'm going to multiply those two also. Well, the 27 and the 3 simplify. So 27 over 3 is 9 times 5 is 45. So the product of those two is 45. Now I'm going to bring back the number that I had in my short-term memory, which was 28. So 28 and 45 is, sure enough, 73, and then 0. And finally, we have 32, and 5 is 37. Wait a minute. 32. Oh, minus 5. Whoa, I got scared for a moment. 32 minus 5, boy, plus 5, that doesn't, I'm panicking right now. Let's see, 32 minus 5 plus 5 is 32, and we don't get 35. 4 times 8 is 32. -3 times 5/3 is -5, but then we're going to add 5 again. So what did I do wrong? Let me double check what I did earlier as I was coming up with this. So you're probably checking your 17827 -3 0 0. Oh, that should be an 8, and I have a 5. Did I just copy that incorrectly from here? Oh, oh, I apologize for this because this happened earlier in the video. I got a 5 here. Where did the 5 come from? That should be an 8. Let's see. 0. So 0, negative 5. Oh, double negative is positive 5 plus 3. There we go. Double negative is 5, but then I missed to add the 3. So that should be an 8. Whoa. It's a good thing that I was double checking, and I apologize because this is a video and we're learning it. You're probably are thinking, wait a minute, that was a 5. Wait a minute, that was supposed to be an 8, and he had a 5, and he kept going. Fortunately, that did not affect the result because we were working with the e's. Remember, we had an u, and the e's are the ones that accomplish those zeros. Whoa. So this should be 8. See, if I was turning this as a test problem, I would definitely want to double check precisely because of what just happened, that I had actually made a mistake. Boy, good thing we did that. So this is this, and by this I mean, all of this is the factoring or factorization of A into a lower triangular matrix. And boy, I'm just going to put a asterisk and continue the asterisk here. This is not very clean. Lower triangular matrix and an upper triangular matrix. Okay, so there we have it, and that is an 8. But there is more to it. Okay, so we are here. Lower and upper triangular, we have the 2. But now we got to split into 3. 3, where this diagonal is a diagonal of 1s, and so is this one. Now, this one already has a diagonal of 1s. 1, 1, 1. Beautiful. This one does not have a main diagonal of 1s. By diagonal, I mean the main diagonal, which goes from upper left corner to the lower right corner of the matrix. So this diagonal is not a diagonal of 1s. It has a 1, that's good, but we have a 27 and an 8. That's easy to fix. So A equals, this one is already beautiful. It is the way we wanted it to be. 1, 0, 4, 5/3, 1. Upper triangular with 1s in the main diagonal. To make those 1s, All we have to do is factor out the 27 and the 8 with matrices. And the way we do that is we put a 1, we factor out the 27, 0, 27, 0. If had that number been not 1, say 17, then we also have to factor out the 17. Had that been something other than 1, for instance, 17. I'm just making up the 17. I hope that I'm not confusing you with that. So, but here we factor out the 27 and we factor out the 8. So 0, 0, 8. So we just have a basic pseudo identity matrix, except that we have 1, 27, and 8 because we're taking those numbers out. But watch out, 1, 7, 8 remains as is. The second row becomes 0, 1, but watch out, we have to divide by 27 because the 27 is being factored out of the whole row. So 27 has to be simplified, or rather, we have to divide the whole row, not just that entry, but the entire row, because when we're multiplying, we're doing this. Um, so the 27 is multiplying the middle row. 27 times 0, 0. And then 27 times 1 is 27. And then whatever we put here is going to be hit by 27. So we have to divide this by 27 so that when we multiply back by 27, we recover the negative 3. Now, 3 over 27 simplifies as 1 over 9. So we end up with negative 1 over 9 because, again, when we multiply with the 27, we recoup back the negative 3. And then this one is easy because we're going to end up with 0, 0. We divide by 8 the entire row, just like this one divides by 27. But when we divide by 8, the only element that is going to be affected is the last one. So that one is not too much of a drama because there's nobody else who's going to be affected. 0 divided by a number by 8, other than 0, is going to be just 0. So there we have it. The above, okay, is the factoring of A into, I'm going to put it bullets so that we can see this a little better, into a lower unit triangular matrix, a lower unit triangular matrix, okay, a diagonal matrix, comma, and an upper unit triangular matrix. Whoa. So it's a long thing, a long statement, but because that is a complicated problem. But we were successful at splitting up, factoring this matrix into 3 matrices: lower with ones, upper with ones, an extra one that is a diagonal matrix. Let's do a second example. See how long it took for the first example? I didn't even start counting checking when we started. I did not check when we started, but I think it took a while to get to this point. So we're going to do a second example. And the second example, A, will be 540. I'm gonna read the rows: 5, 40, 45, 10, 86, 84. I'll show you how I came up with this in a moment. 15, 144, and 118. Okay, so our goal is to, and maybe we can take a couple of shortcuts. Perhaps we can take a couple of shortcuts. But we got to be very, very careful, and we have to double check our work and our computations. Remember, our goal is to split that into 2, to further split up into 3. And we're going to do this by elimination. Oh, before I continue, let me, sorry to interrupt myself. I wanted to back up a little bit because I did mention there were 2 ways to go about this. And I'm thinking not to do the second way. So the way we went about this process was we found each one of the inverses, we multiplied the inverses, and then we got our L. Remember how we did that? We checked that we had our inverses by actually checking, and then we multiplied the inverses. There were 3 of them. This one was waiting while we were multiplying those 2, and there was our lower triangular matrix. But there's a second way to go about this. We could multiply those 3 instead of multiplying the inverses, multiply the e's. So these are the e's, and these are the inverses of those e's. And what we did is multiply those together, and voila. And we got our, so multiply the 3, and there's our lower triangular matrix. But there is another alternative. There's an alternative to that. So let me write down real quick the alternative. The alternative is starting from this, E3, E2, E1, A equals U. Multiply them without finding the inverse. So skip the step of checking. Yeah, don't do the inverses. Just multiply those 3, which we already got from this step. Yep. So multiply them together without finding the inverses. You're going to get a big giant E. And then take the inverse of this. And that's going to give us exactly the same answer. The same L. We're going to end up with the same L. Yeah, and you can use Gauss elimination to get the inverse. So I'm not going to go over that because it was already a long problem to start with. But yeah, perhaps we can do this in the next example this way. We will see. Okay, so there's our A. I'm going to save some time. Instead of simplifying this column 1 element at a time, or getting rid of those 2 numbers 1 number at a time, let's do it in one shot. Okay, so notice that this is not a 1. So we're going to come up with an elimination matrix that is going to get rid of this 10 and this 15 using the 5. So we have to take away twice this guy to get 0 here, because 10 is twice as much as 5. Take away 2 of the first row. Take away 3 of the first row to get rid of the 15. And then keep everything else. Well, I shouldn't say keep everything else. We're going to add the second row, twice the first row, add it to the second row. That kills this 10. But that's it, don't do anything else. And then negative 3 times the first row, add it to the last row. The last row is going to get rid of this guy. So we're going to multiply this, which we're going to label as elimination matrix number 1. Yeah, and that's going to annihilate 10 and 15 at once. Now watch out. Those numbers are going to be not the same anymore. 5, 40, 45. That's a 40. Because it kind of looks like, since I put a big space in between, kind of looks like 4 and 0, but it's 40, so that's why I put a line in between. 10, 86, 84, 15, 144, 118. All right. So we got, this is just the first row, 5, 40, 45. Second row, negative 10 plus 10, 0. But the 86 will be changed as well. Negative 80 plus 86, 6. Negative 90 plus 84. Whoops, sorry. Negative 90 plus 84 and plus 0. Back here, by the way, I neglected to say that. Negative 80 plus 86 plus 0. Negative 90 plus 84, that's negative 6 plus 0. Negative 15 plus 15, 0. Negative 120 plus 144, 24. Negative 135 plus 118. I'm thinking 135. I'm going to try 17. 17. Yeah, I think that 17 is 1. But it's got to be negative, isn't it? Negative 135. Negative 118. Yeah, plus 118. Yeah. Negative and a positive, but the negative is bigger. Anyway. Yeah, that should be it. Negative. Anyway, we'll check our solutions at the end. If I'm making a mistake, please bear with me. All right, that's the first elimination matrix. And we get this matrix is not upper triangular matrix, but it's closer to an upper triangular matrix because it has 2 zeros, and we want one more 0, and voila, we gotta get clear this guy. Okay, let's try to do this in here. So this is a new equation. Please don't put equals when there's no equals. That's a bad habit to get into. So maybe put a comma if you want to. You don't have to, but we are starting a new equation. Okay, so we want another elimination matrix that multiplied with this matrix we got now will clear off the 24. Keep in mind that we have a 6 because it is tempting to do 1 0 0 0 1 0 0. Oh, I'm just going to put a negative 24. No, watch out. This is a 6. So we need to multiply by negative 4, the 6, to get negative 24. And when we add the 24, then we end up with 0. And then, yeah, that means we're going to add one of those. So this is a new equation. This is what we claim is E2, the second elimination matrix that clears off the second, this column, so we have a 0 there. So we're going to multiply by 4, 5, 40, 45, 0, 6, negative 6, 0, 24, negative 17, and see what we get. Okay, so the first row, leave it alone. 5, 40, 45. Second row, leave it alone. 0, 6, negative 6. Third row, don't worry about this row. So 0, 0. 40, no, that's 0. Negative 24 plus 24, 0. Yes, that's what we wanted. Nothing. Positive 24 minus 17. I think that's 7. Okay. So we are not there yet. We got U. We got the upper triangular matrix. All right, but we want A to be broken up into an upper triangular matrix and a lower triangular matrix, but we don't have the lower triangular matrix. And multiplying those two won't do it because those two multiplied together with A, multiplying A with it is what got us here. So this is what we have so far. A, when we multiply E1 and E2, this E1, and this E2 in that order, watch out because we multiplied first E1 and then E2. So when we read this from left to right, We are multiplying E2 and then E1 and then A. That gives us the U. Now let's multiply those two, and we're going to get a giant E, a big elimination that clears off a bunch of entries all at once. Now, we're going to multiply E2 and E1 in that order. E2, it's still here, the ink still fresh in this piece of paper, has a -4 here. So 1, 0, 0, 0, 1, 0, 0, -4, 1. And we're going to multiply, so that was E2 with E1. I still remember E1. It had a -2 and a -3. 1, -2, -3, and then the rest is identity. Okay, I'm going to try to squeeze that in here. Hopefully it will fit. So first row, leave it alone. Second row, yeah. Second row, -2, 1, 0. Third row, 0. Boy, I better do this carefully. Let me double check the first rows. So pick 1, 0, 0. Yep. -2, 1, and 0. Yep. 0, 8, -3. Oh, we gotta be careful with this. 0, 8 positive, -3. 5, 0, -4. 0, 0, 1. Whoa. Now, I'm using a different method that we did before in the example 1. In example 1, what I did is we found the inverse of this, we found the inverse of that, which would go here, and then we multiply the inverses. Remember, here we're not multiplying the inverses. We're multiplying straight out the e's. And this is unexpected. Let's double check. 1, 0. Oh no, I'm going to multiply those. This row and this column. And this was E2. And our E2, yeah. So we end up with 0, 8, -3, 5. Yeah, that's the way it is. Okay. So this is our giant E, this matrix. So right now what we have is EA equals U. If we multiply this guy with the original A, we're going to end up with the upper triangular matrix, this one. So if we multiply our original one with this guy, we're going to end up with this. And it's not a bad idea to double check. There's a lot of matrices going on here. But I don't want that. I want A to be something times U. So we have to find the inverse of E. And here's where I'm going to use the Gauss-Jordan elimination method. Remember how that goes? So I'm going to use the Gauss-Jordan elimination. So start with this matrix, 1, 0, 0, -2, 1, 0, 5, -4, 1. Well, we want to put 1, the identity matrix next to it. This should be a review problem from the previous video. And don't neglect to learn linear algebra. All right, so we're going to perform what is called row operations to transfer this into here. So we want to get rid of this guy. And the way we can get rid of it is by, I'm trying to think. We can take the second row no, take the second row and add twice the first row. So we're gonna take the second row and add twice the first row. This guy, add two of those, and that puts a 0 in here, because our goal is to get an identity matrix here. So we're gonna get a new matrix. Okay, so the first row is not affected. 1, 0, 0, 1, 0, 0. So two of those plus this, 0. Two of those plus that, 1. Two of those plus that, 0. Two of those here, 2. Two of those there, two of those there. While we do that, why don't we take care of the 5? So take the third row and take away 5 times the first row. Okay, 5 minus 5, 0. Negative 4 minus 0, negative 4. 1 minus 0, 0. 0 minus 5, 0 minus 0, 1 minus 0. Okay. So now well, here this should be a 1, because 1 minus 0 is 1. There. Okay. So now we need to add 4 of those onto here. So row 3 plus 4 row 1s will clear this guy. So the first 2 rows remain the way they are. 2, 1, 0. And now we're going to add 4 of those onto this. So 4 1s. No, I'm sorry. Did I put row 1? I meant row 2. Yeah, because otherwise we're going to mess this 0 up, and we want to end up with an identity here. So 4 of those here, nothing. 4 of those there, 0. 4 of those there, 1. 4 of those here, 3. 4 of those here, 4 and 1. So it looks, so E is the matrix 1, 0, 0, negative 2, 1, 0, 5, negative 4, 1. We claim we found the inverse. The inverse would be this guy, 1, 0, 0, 2, 1, 0, 3, 4, 1. Did we find the inverse? Well, that's easy to check. We can multiply out. 1, negative 2 plus 2, 1, 0. 5 minus 8, 3, negative 3 rather, plus 3. Whoa, I got scared for a moment. So 5 plus 3 is 8, minus 8 is 0. 0, negative 4 plus 4, 0, 1. So sure enough, this is the inverse. So remember our equation, EA equals the upper U. Well, we found E inverse, so which is this guy. It's a lower triangular matrix. So A is equal to, if we multiply by the inverse on both sides of this equation, we get on the left E inverse U, and we're just going to relabel this guy as L. L. So they're the same matrix, U. So A can be written as 1, 2, 3, 1, 2, 3, 0, 1, 4, 0, 0, 1 times Where's our U? Remember, U is here. 5, 40, 45. 0, 6, negative 6, 0, 0, 7. So this is the factoring. Yeah. The above is the factoring of matrix A into a lower triangular matrix and an upper triangular matrix. It's not a bad idea to double check, because the multiplication of those two should give us this. The first row is good. 10 is fine. 46, yep. 90, 84, yep. And then we get 15, 120, and 24, yep, 144, 135 minus 24, yep, 111, plus 8, 118. Yep, so it works. I just double checked that those two multiply together. This is a lower, this is an upper triangular matrix. Multiply together give us exactly this matrix. So we have succeeded. This is correct. It's accurate. I'm going to be asking you to do one other thing, to factor A into 3 matrices. Now, if these guys were already 1, 1, 1, 1, then if I ask you to factor into 3 matrices, a lower triangular, an upper triangular, and a diagonal, then you don't have to go any farther. You can just say, well, there it is. The diagonal would be the identity. I suppose you could do that. It would be a little bit trivial, because we're not adding more information when we multiply by an identity. So the reason why we need a diagonal, so bear that in mind, the reason why we need a diagonal is because it is desirable to have ones in the main diagonal, to have a unit triangular an upper unit triangular matrix, as well as a unit triangular, a lower unit triangular matrix. So this is once already. And because of the way we are constructing our elimination matrix, this is always going to be the case. This is not necessarily always the case. So we have to, we have to split that into 2 more matrices. Okay, so this one matrix, leave it alone. 1, 0, 0, 2, 1, 0, 3, 4, 0. We're going to factor 5, 6, and 7. Whoa, it's got to be a matrix. We don't factor that way. That was silly in my part. 5, 0, 6, 0, 0, 0, 7. That's the way we factor 5, 6, 7 from the main diagonal. We don't just put a column. That was very silly. And then when we factor 5 out of this, we're going to end up with 1, 8, 9. Factor 6 out of that, 0, 6. Whoa, we just factor 6. I guess that shows that I'm very impulsive, because I can't wait to put the number. So 1, negative 1, and then 0, 0, 1, 0, 0, 1. There. So now we got a perfect diagonal. I mean, by perfect, I mean ones. Let's see. So when we multiply, let's triple check. So 5, 40, 45. Yep. and then 0, 6, -6, and then 0, 0, 7. Yep. So this, the above, is the factoring of A into, and here I'm going to, this could be a paragraph, but I want to emphasize the three kinds of matrices we have. We have a lower into lower unit triangular matrix times, well, these are bullets, they're not times, but times a diagonal matrix. I should have put an article here. A lower unit triangular matrix, and I've missed to put, oh, lower, yeah, it is the lower, yep. A diagonal matrix and an upper unit triangular matrix. There it is. It would be better if A was actually written like so. But it doesn't quite fit. So, but this is the factoring. All right. How did I come up with a matrix? Because this is just a made-up example, an example I just made up. This is just the example. Well, I started backwards. I just wanted to show you how I came up with the matrix. I started out by a diagonal. Whoa, there's a typo here. Good thing I'm checking this. There. So there's a diagonal of ones, and I just start putting numbers, 2, 3, 4. And then 5, 6, 7 for my diagonal. So I started backwards. I started out by what I wanted the factors to look like. I wanted them to start with, I didn't want to use a 1 because we already have several 1s. So I started out with 2, 3, 4, 5, 6, 7, 8, 9, and I didn't want to have a 10. So I started out with 1, but I didn't want to have a 1. So I continued with -1. So this is just the way I did it myself. So this is the way I came up with this problem. I worked backward with the actual factoring. I started with the actual factoring, and I just put some random numbers. They're not really random because they're sequential, but call them random. So 2, 3, 4, 5, 6, 7, 8, 9. I didn't want to put a 10, and there it is. And then I just multiply them carefully. Multiply those two by hand, multiply the rest by hand. And that's how I obtained the example, 5, 40, 45, 10, 86. So I designed the example so it would break up into, those nice matrices. All right, so we're going to stop the video. 70,009 here.